Units and dimensions. Units and dimensions. Physical quantity represented by an expression. What is the physical quantity represented by L square by 2E? L is angular momentum, E is energy. We will get the relation as ml square, which is the dimensional formula of moment of inertia. Dimensional formula of L angular momentum is ml square t to the power of minus 1, ml square t to the power of minus 1, and that of energy E is ml square t to the power of minus 2, ml square t to the power of minus 2. Therefore, L square by 2E becomes m square t to the power of 4 L to the power of minus 2, m square L to the power of 4 t to the power of minus 2 divided by m L square t to the power of minus 2. On simplification, it becomes ml square, which is the dimensional formula of moment of inertia. So, L square by 2E is moment of inertia. What is the dimensional formula represented by E square by 2 epsilon naught Ch? E square by 2 epsilon naught Ch. E is charge, epsilon naught permittivity, C velocity of light, H Planck's constant. E charge, epsilon naught permittivity, C speed of light, H Planck's constant. Dimensional formula of E is at, that of epsilon naught is m to the power of minus 1 L cube t to the power of 4 a to the power of 2, epsilon naught m to the power of minus 1 L to the power of minus 3 t to the power of 4 a to the power of 2, C L t to the power of minus 1, H ml square t to the power of minus 1, ml square t to the power of minus 1. E square is a square t square, E square is a square t square, epsilon naught Ch is m to the power of minus 1 into L to the power of minus 3 into a to the power of 2 into t to the power of 4 into L t to the power of minus 1 into ml square t to the power of minus 1, and simplification gives a square t square, a square t square. On simplification, E square by 2 epsilon naught Ch, it becomes m to the power of 0 L to the power of 0 t to the power of 0. Since E square is a square t square, epsilon naught Ch is a square t square. So, E square by 2 epsilon naught Ch will be m to the power of 0 L to the power of 0 t to the power of 0, that is dimensionless constant, dimensionless constant. Derivation of a relation using dimensional analysis. For example, let us take kinetic energy. Let us suppose that kinetic energy is dependent on mass and velocity. Let us suppose that kinetic energy depends on mass and velocity, and let us derive the relation for kinetic energy. Let us suppose energy is proportional to m to the power of a v to the power of b, where m is mass, v is velocity. So, E is proportional to m to the power of a v to the power of b, or m L square t to the power of minus 2, m L square t to the power of minus 2 is proportional to m to the power of a into L t to the power of minus 1 whole to the power of b, m to the power of a into L t to the power of minus 1 whole to the power of b, or m L square t to the power of minus 2 is proportional to m to the power of a L to the power of b t to the power of minus b, m to the power of a L to the power of b t to the power of minus b. By comparing the powers, you will get a is equal to 1, b is equal to 2, a is equal to 1, b is equal to 2. That means E is proportional to mv square. We can only derive the relation E is proportional to mv square, but actually E is equal to half mv square. That constant half can be determined only by experiment, but not by dimensional analysis. Dimensions of a constant in an equation. Let us take the equation V is equal to a by b into a by b into 1 minus e to the power of minus tb, 1 minus e to the power of minus tb. Tb is power, it is exponential, hence it has no dimensions. So, tb is dimensionless, so it is 1 or m to the power of 0, l to the power of 0, t to the power of 0, etc. Hence, it is 1. So, the dimensions of b are 1 by t or t to the power of minus 1. b is t to the power of minus 1. Then a by b is velocity, v is velocity. So, a by b should also be velocity. So, it is L t to the power of minus 1. A by b is L t to the power of minus 1. So, a is equal to b into L t to the power of minus 1, but b is t to the power of minus 1. Hence, a is L t to the power of minus 2. The dimensional formula of a is L t to the power of minus 2. Assumed fundamental physical quantities. Assumed fundamental physical quantities. Let us try to express length in terms of c, g, h. C is speed of light, g is gravitational constant, h is Planck's constant. Let us try to express length. That means, we are taking speed of light, universal gravitational constant and Planck's constant as our fundamental physical quantities, and let us try to express length in terms of c, g, h. Let us suppose L is equal to g to the power of a, c to the power of b, h to the power of c. Length is g to the power of a, c to the power of b, h to the power of c. The dimensional formula of g is m to the power of minus 1, L to the power of 3, t to the power of minus 2. The dimensional formula of c is L t to the power of minus 1. The dimensional formula of h is ml square t to the power of minus 1, ml square t to the power of minus 1. Let us substitute these dimensional values, the dimensional relations, then we get L is m to the power of minus 1, L to the power of 3, t to the power of minus 1 whole power a, m to the power of minus 1, L to the power of 3, t to the power of minus 2 whole power a into L t to the power of minus 1 whole power b, L t to the power of minus 1 whole power b, ml square t power minus 1 whole power c, m L square t to the power of minus 1 whole power c. On simplification, L becomes m to the power of minus a plus c, m to the power of minus a plus c, L to the power of 3a plus b plus 2c, L to the power of 3a plus b plus 2c, and t to the power of minus 2a minus b minus c, t to the power of minus 2a minus b minus c. Comparing the powers on both sides, from the powers of m we get minus a plus c is equal to 0, minus a plus c is equal to 0. Comparing the powers of L, we get 3a plus b plus 2c is equal to 1, 3a plus b plus 2c is equal to 1. Comparing the powers of t, we get minus 2a minus b minus c is equal to 0, minus 2a minus b minus c is equal to 0. Minus a plus c is equal to 0 gives a is equal to c, a is equal to c. Minus 2a minus b minus c is equal to 0. From this, by substituting a as c, we get minus 2c minus b minus c is equal to 0. Substituting c for a, we get minus 2c minus b minus c is equal to 0, or b is equal to minus 3c, b is equal to minus 3c. We have the relation 3a plus b plus 2c is equal to 1, 3a plus b plus 2c is equal to 1, but a is equal to c and b is equal to minus 3c. By using these two values, we get 3c minus 3c plus 2c is equal to 1. 3c is for 3a, minus 3c is for b, and then plus 2c is equal to 1. Hence, 2c is 1 or c is equal to half. 2c is 1 or c is equal to half. Since a is equal to c, a is also equal to half. A is also equal to half. B is equal to minus 3c. Hence, minus 3 into 1 by 2, that is minus 3 by 2. B is minus 3 by 2. 2c is equal to 1 or c is equal to half. So, a is equal to half and b is equal to minus 3 by 2. On substituting, we will get L is equal to z to the power of half, c to the power of minus 3 by 2 into h to the power of half, g to the power of half into c to the power of minus 3 by 2 into h to the power of half, or L is equal to square root of g h by c cube, square root of g h by c cube. Conversion of units from one system to another system. The relation that we use is n1 into m1 to the power of a into L1 to the power of b into T1 to the power of c is equal to n2 into m2 to the power of a, L2 to the power of b, T2 to the power of c. n1 into m1 to the power of a into L1 to the power of b into T1 to the power of c is equal to n2 into m2 to the power of a, L2 to the power of b and T2 to the power of c. Let us try to convert 10 newtons into dynes. How many dynes do we get for 10 newtons? Dyne and newton, they are the units of force. So, the dimensional formula for force is m to the power of 1, L to the power of 1, T to the power of minus 2, m to the power of 1, L to the power of 1, T to the power of minus 2. So, we can express n1 m1 to the power of a, L1 to the power of b, T1 to the power of c is equal to n2 into m2 to the power of a, L2 to the power of b into T to the power of c as 10 into kg to the power of 1, n1 is 10 and m1 is kg, kg to the power of 1, L1 is meter. So, meter to the power of 1 into second to the power of minus 2, t is second, second to the power of minus 2, that is equal to n2 into, let us take dyne is the unit in CGS system. So, m is gram, L is centimeter, T is second. So, gram to the power of 1 into centimeter to the power of 1 into second to the power of minus 2. The left one is taken as SI system, the right one is taken as CGS system. Hence, N1 is 10, M1 is kg, L1 is meter, T1 is second, N2 is dyne, M2 is gram, L2 is centimeter, T2 is second. But 1 kg is 1000 grams, 1 meter is 100 centimeters, 1 kg is 1000 grams and 1 meter is 100 centimeters. Hence, we get 10 into 1000 grams into 100 centimeters into second to the power of minus 2 is equal to n2 into gram into centimeter into second to the power of minus 2. Gram into centimeter into second to the power of minus 2, it gets cancelled, Therefore, n2 becomes equal to 10 to the power of 6, 10 to the power of 6. So, 10 newtons is equal to 10 to the power of 6 dynes. N1 is 10 newtons. So, N2 is 10 to the power of 6 dynes. So, 10 newtons is equal to 10 to the power of 6 dynes. Verification of a relation. Verification of a relation. Let us take the relation Sn is equal to u plus a into n minus half. Sn is equal to u plus a into n minus half. U is velocity, initial velocity. So, its dimensional formula is Lt to the power of minus 1. Sn is displacement in the nth second. Since it is displacement in 1 second, it is also velocity Lt to the power of minus 1. N is time in seconds. Acceleration is Lt to the power of minus 2. So, the last term is At. Acceleration into time. Acceleration into time. Therefore, it is equal to Lt to the power of minus 2 into t. Lt to the power of minus 2 into t, that is Lt to the power of minus 1. Lt to the power of minus 1. Constants. Some constants have dimensions. For example, Planck's constant h, universal gravitational constant g, universal gas constant R, Boltzmann constant K, etc. Some constants have dimensions H, capital G, R, C, K, etc. Some physical quantities have no dimensions. Some physical quantities have no dimensions. For example, angle, strain, relative density, etc. Angle, strain, relative density, though they are constants, they do not have any dimensions. Application of dimensional analysis. Application of dimensional analysis. Dimensional analysis is used to check the correctness of an equation. To check the correctness of an equation. 2. To convert units from one system to the other. To convert units from one system to the other. 3. To derive the relationship between different physical quantities. To derive the relationship between different physical quantities. Limitations of dimensional analysis. Limitations of dimensional analysis. 1. The value of proportional constant cannot be determined. The value of proportional constant cannot be determined. 2. Equations containing trigonometric, logarithmic and exponential functions cannot be analyzed. Equations containing trigonometric, logarithmic and exponential functions cannot be analyzed. If a physical quantity is sum or difference of two or more physical quantities, if a physical quantity is sum or difference of two or more physical quantities, we cannot use this analysis. We cannot use this analysis. If the proportionality constants have dimensions, we cannot use this method to derive the relation. If a physical quantity is dependent on more than three fundamental physical quantities, this method becomes complicated.